This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
All right, so the final speaker of the session is Jens Eisert again. And so they're really squeezing you for all you got. And so Jens is going to talk about continuous variable tomography. And with that, take it away.
Yeah, thanks very much indeed. That's great. Yeah, my name is Jens Eisert. I'm a PhD student in the Berlin team. And it's my great pleasure to present a result that we did together in quantum learning theory that we are particularly excited about, which is to think about continuous variable tomography being strikingly difficult and other themes in learning theory. Now it's very difficult to deny that discrete variable qubit-based quantum information processing has come a long way since it was first conceived in the 1980s by Feynman, Benioff, Deutsch, and others. We now have an over 1,000 qubit quantum computer available. And this name already gives it away in that when we think of quantum computing, we usually think of devices set up or made out of qubits, so the Hilbert space would be like C2 to the power of n. That said, natively, many, if not most, quantum systems are actually infinite dimensional. We just rather look for a couple of levels of a bigger system when we think of discrete level systems in one way or the other. Say, think of modes of light. They're just basically collections of harmonic oscillators that are labeled by frequencies. You can think of optomechanics in the quantum regime, microwaves for superconducting qubits. These are all equipped with infinite dimensional Hilbert spaces. In fact, you might not know that chips of this type that I mentioned earlier, or that my other me mentioned earlier, the Sycamore chip is actually both a discrete and continuous variable system in that the quantum circuits that we know, the random quantum circuits on the one hand, and analog quantum simulation of many-body localization, you name it, they actually run on the very same chip, just using a different kind of encoding. Now, continuous variable quantum information processing, in particular, when we think of modes of light, is extremely well developed in its state manipulation, in particular when we have like for passive Gaussian operations, linear optical arrays available or integrated optical circuits that can be done to extraordinary precision. Also, we have good sources with very high efficiency that spit out states of light with high mode quality, and good detectors, which I give 3 examples of this type. We often think of homodining, where the light comes in and there's a strong oscillator coming down on the other port, and then you subtract the photocurrent. So that's basically a measurement of X, of P, or any line in phase space. You can do like double homodining, like heterodining. That's basically realizing P of M elements that are over complete sets of coherent states, or 0, 1, 2, 3, 4, 5. You can count photons. Now, in particular, the former two can be done to extraordinarily high efficiency. Counting is also reasonably good. So that's continuous variable quantum information. There's also some applications that are really tailored to that regime. For example, we love random circuit sampling, but there's also Gaussian boson sampling. That's the continuous variable sister of random circuit sampling, where you feed in Gaussian states and make appropriate measurements, but end up with similar claims of a quantum advantage, formerly known as quantum supremacy. In fact, one can argue that the setting here with 50 squeezed states and 100 modes, as done by the Han Zhanwei group in China, is like larger in a way than what's available for quantum circuit sampling. Also, the GKP states and quantum error correction that Xanadu is pursuing, that's also a continuous variable system, obviously. In quantum key distribution, the fact that we have these nice sources available and the good detectors argue that it makes a lot of sense to think of continuous variable system. There's an entire field called continuous variable quantum key distribution. So that's my 4-minute tutorial on continuous variable quantum information. But here and there and everywhere, predictive power means that we have to do extremely accurate benchmarking. We cannot hope to scale up quantum architectures without having precise understanding of our individual components. That's the topic of certification and benchmarking, where we really go into the lab. I'm not making the same joke again. And take data, and then you want to kind of certify that you've done the right thing. We've written a review article in the Reviews of Modern Nature, Reviews Physics, where we have figure 1 that basically explains a couple of techniques of certification and benchmarking according to the assumptions one is willing to make and the information gain one is hoping to get. In the left lower corner, there's self-testing, where you make very few assumptions, just causality basically, but you also learn quite little. On the high up end is learning the full quantum state from data, an unknown quantum state, or also partially known quantum state from data, ARCA quantum state tomography. That's routinely done from data in the labs worldwide, where people go into labs, take data, and learn partially unknown quantum states, surely in the discrete variable setting, but also in the continuous variable setting. Actually, that's even where this all started from. The first tomographic experiments were done in the continuous variable world. So, in this light, I ask a question that's ridiculous in this setting, given that this was done in ancient times, namely, can we reasonably hope to reliably perform quantum state tomography in continuous variable system? What? I mean, this is what people have been doing all along. That's where the field comes from, ultimately. But still, I will dedicate the main part, which will be short, don't worry, on namely this being kind of strikingly difficult. So what does one do? In standard continuous variable tomography, you have like n modes of light, like n harmonic oscillators, and they are equipped with a so-called characteristic function. That's the expectation value of the shift or the Weyl operator that's giving rise to a complex valued function. This has a symplectic Fourier transform. That's the Wigner function. That's as close as it gets to a probability distribution for quantum systems. They are real valued. They are normalized to 1, but they can, but don't have to, dip under 0 either way. Now, what one usually does in quantum state tomography is that one measures along lines, or does homodining along lines, like all these projections, and does these projections for different lines, and then recovers the two-dimensional Wigner function, ARCA, the quantum state, from this. So one recovers the approximation of rho via an inverse Radan transformation, and when you think that, what is this tomography doing? When you do like a nuclear spin resonance thing in medicine, that's doing precisely the same thing, where you recover a higher dimensional object through lower dimensional slice. That's where the name tomography even comes from, if you're not aware of that. This is the plain vanilla thing. There's similar schemes for heterodyning. If you look at the citations, it was 1905. There was already a review by Ulf Leonhardt, like measuring the quantum state of light. There was a dusty review already at the time. I wasn't even born then, so that was a long time ago. Wow. Okay, that's good. It's very good, but it's not good enough for our like modern, more rigorous perspective, where we want to have guarantees, we want to have trace norm bounds, we want to have certificates, we want to know what sample complexity you need to have to learn something. So can we get rigorous trace norm bounds for continuous variable tomography, as we are all used to in the quantum information world? 9 minutes. I have only 3 results to offer here. And this will be along the lines of like, what is the sample complexity to recover in one norm? You want to have a guarantee. How many shots do you need? How many samples do you need to get a guarantee that you're close in the operationally well-motivated one norm? And there's 3 specific results. The first one is the most important one, which is Oh, no, here. That's one thing I said before. For finite dimensional systems, that's well understood. In that, general tomography requires of the order d squared over epsilon many copies, where d is the dimension of the system. Epsilon squared comes from the Hefting bound. If you have the additional guarantee that you are close to being pure or low rank, then this requires of the order d over epsilon many copies. You square root the d squared to d and get away with a smaller effort. If you have like additional structure, like matrix product states or so, there's also alternative verification methods available that work a bit better. Now, some time ago, we also joined forces with our friends in Innsbruck, doing like a low rank 4 recovery of a system in a 2 to the power of 7 dimensional Hilbert space, actually doing an ion trap quantum state tomography experiment sometimes ago. Good, but how is this for continuous variable systems? And now comes the main result, the first main result, which is continuous variable tomography is strikingly difficult. So for an unknown state that satisfies a kth moment constraint, of which the first moment constraint is maybe the most important one, for k equals 1, n is the number operator, it just means that the energy expectation is finite. It's not a cutoff, you don't chop off the fog layers, but you just say at some point you have to pay the bill of your nuclear power plant provider nearby, because that's the energy that you are investing in the preparation in one way or the other. There's some energy in the system providing such a constraint. The number of copies